All right. Okie dokie, let's go ahead and we can get back to talking about matter. So, matter. Yesterday we talked about classifying it. So, we talked about classification. We talked about how to classify matter. We did that as pure substance versus a mixture, and we looked at some of the kind of the subdivisions there. We also talked about properties, various physical or chemical properties matter might have, and we also talked a little bit about changes. And so we were able to see, if I were to change one of the physical properties, that's a physical change, and if you and it doesn't change the substance itself, but if you do a chemical change on it, you're fundamentally changing the chemical makeup of whatever whatever matter you're messing with. So that was kind of yesterday. So today we have just kind of one last bit. Again, I'm yellow. What is happening here? I move the curtains slightly and then I'm back to normal, or yeah, go figure. Okay. It's crazy. All right, that annoys me for some reason, but that's okay. Today we have just a little bit more about matter to talk about, and then we will talk a little bit about energy, and then we'll start talking about numbers. I'm sure all of you are excited to start talking about the math aspects of this class. So, let's go ahead and talk a little bit about the states of matter. Again, this is a physical property. Of matter, whatever state it happens to be in. And since we have all, gone through elementary school, we all know that we essentially are dealing with primarily three states of matter. Of course, there are others: supercritical fluids, plasmas, things we don't need to worry about. For us, we just worry about the main three, the ones that we're going to likely encounter in everyday life. The others you might encounter with kind of special circumstances. And we're just going to go ahead and put out some characteristics about these states of matter, things that are pretty obvious to us, hopefully, and we'll go from there. So, when we're talking about solids, we can stay with dark blue. Solids, we can kind of define a solid as having a definite shape and a definite volume. Meaning that at any given time, your solid of interest will have its shape, and that shape does not change. And it also occupies the same amount of space no matter where it is. Here is, I don't know why I'm choosing this, but I have a stapler here that is in fact in the solid state. If I move it over here, a different physical change, it's still a stapler. It's still got the same shape, stapler shape, I suppose, and it's still occupying the same amount of space no matter where I put it, right? So that's what defines a solid. A liquid, by contrast, will have an indefinite shape. That means its shape will change depending on its kind of local environment. And this is one thing you can do if you have small children or no small children. You can mess with them with the next property that we're going to talk about, which is the definite volume. So liquids, like water, will change their shape, but their volume will be the same. So they'll still occupy the same volume no matter what container you put them in, but their shape will just adapt to that container. And so with messing with little kids, As part of like kind of they develop psychologically as their brains develop, uh, while they're still young, you can trick them by pouring water from, say, a short, wide glass into a tall, narrow glass, and the child will think that there's more water in the taller glass. It's just part of our developmental psychology. And so, despite the fact that water, the volume is exactly the same, give or take a drop if you spilled one or whatever, but just seeing the taller shape with their brains, they'll think it's more. So you can bamboozle them that way, and it's kind of fun to see that in process in reality. So, but we know liquids will change their shape based on their containers, but their volume will be the same. So that's that kind of characteristic there. Gases, on the other hand, have neither a definite shape nor a volume. Gases will always expand to fill whatever container they're in. So your container size will determine the volume of your gas. So if I take a balloon, which I do not have right now, but imagine a balloon. I have a certain amount of gas in there, whatever it is, helium or just air or whatever. If I pop that balloon, all those gas molecules inside are just going to spread around to my room, essentially. They're going to just expand until they fill the container that they're with. So gases do not have a defined volume. Their volume will always be equal to whatever container they're in. So gases are kind of different there. So we can see here, these are kind of the main characteristics that are going to distinguish these states of matter. But we can say a few more things about them, more kind of observational things. For example, solids are typically rigid, meaning they're pretty tough. They don't bend easily. They're hard, you might say. Not all solids, of course. You have something like a marshmallow, which is a solid, not necessarily rigid, right? But by and large, most solids are. When we think of solids, typically we think of rigid things. With liquids, those flow and pour fairly easily. Same thing with gases. You can flow and pour your gases pretty easily. Although typically they'll just go ahead and get out of there. Unless you're working with a really heavy gas, typically gases will just all mix together. But you can technically you can make gases flow pretty easily. Ducting systems, air conditionings, all that, you have gas flowing through those. Just air, most likely. Or if it's in like your refrigerator, you have like pentane or some other coolant in there. But those gases are easily flowing through some tubes. Let's see, what else do we have? Solids are typically incompressible, which means you can't squish them to make them smaller very easily, to make them take up less space. Some solids, yes, like a sponge or something like that, yeah, you can kind of compress them, but that's kind of not an ideal solid. If we're thinking about the stapler, if I'm really squishing it, like, look how hard I'm squishing it. But it's not compressing, right? Solids don't typically compress very easily. Neither do liquids. We can't really do that. And note, both of these have definite volumes already. So trying to squish them into smaller volumes doesn't really work. Right? They already have their defined volumes, so we can't really change those very easily. But gases are super compressible. We can put an enormous amount of gas into a container. So we can really mess with the volume of a gas. Again, because they'll take the shape of their container and volume of their container, we can just keep throwing in more and more gas to the same container, thereby compressing it. What else do we have? These are solids are relatively dense. So are liquids. By dense, I mean that they have a relatively large mass for their volume compared to gases, which are not dense. Gases do not weigh very much for a given volume. You might think of like how heavy this is. You know, that's the whole pound of feathers versus pound of bricks or whatever. Bricks are more dense than feathers are, right? But both of those are solids. They're still fairly dense. If you compare it with the density of air, solids, liquids tend to be, 1,000 times more dense than air is. So gases are going to be less dense than the other two. And then finally, if we are kind of looking molecularly or atomically at solids, liquids, and gases, we're going to see that solids can be crystalline or amorphous. Amorphous. By crystalline, I mean we have these nice, orderly kind of atoms, nicely organized, and they're just kind of vibrating in place. They don't really move. They just kind of sit there vibing, right? They're just having a good time. Amorphous solids are less organized. So they might have gaps or something in them. But they're also not moving. They're just vibrating. So they don't move side to side. They don't move on top of each other. They just kind of vibrate in place. So amorphous, they kind of just lack a repeating structure. Crystalline ones have kind of nice repeating structure. But those are both solid. So nothing's really moving atomically. They're just vibrating in place. So they still have some energy. They're still vibrating, but they're not actually like moving left and right. Liquids, though, do, in fact, move around each other. And we're going to see that the atoms or molecules in a liquid are constantly zipping around. Not really zipping around, but they're always in motion. So they're able to move translationally. Oh my gosh, we have a spam already. Ignore that. No matter how many times I try to adjust the spam filter on this, they still decide to get through. So never click any mystery links in chat. So this is the equivalent of our Zoom bombing, right? Where people just come in or whatever. So ignore those. So liquids can they move around. We call this translational motion. So they can move from left to right, up and down, in and out. They can move in any direction they want, and that's translational motion. So they can just move from place to place. They're not just vibrating in place there. And gases, on the other hand, are super spread out, and they are moving very quickly all over the place. So they are constantly moving rapidly. So hopefully just kind of the size of the arrows there compared to the liquids. You can see they're moving more quickly. They're spread out as well. That's how we can kind of see this density property. So we see that all these solids and liquids, the atoms are close together. So they're dense. there's a lot of them in a given space. But the gases, on the other hand, they're really far apart. They're moving constantly, so they are not really. It's going to be not dense as a result. Uh, movement is random. So at least, if they're just kind of sitting there. If you are flowing a liquid or a gas through a tube, you can totally do modeling to predict if you're going to have turbulence or not. So a lot of kind of fluid dynamics engineering deals with being able to make sure that liquids and gases can flow in a laminar manner. That means not turbulent, where everything is flowing nicely. So having the correct speed and the correct diameter of your tube can be kind of calculated by a computer to make sure that everything's going to flow nicely with advanced kind of modeling of this motion. But if they're just sitting there, it's totally random. So they call it Brownian motion, just random movement of molecules or atoms as they go around. So so it just depends. If you're forcing it to move in a particular direction, you can model it. If it's just sitting there, it's random. So, all right. Cool. All right. So that's we're kind of gonna leave this topic now. We'll come back to it later on in the semester when we talk about gases, liquids, and solids towards the end of the semester. The 101 students will have it a little bit earlier than the 111s, but we'll be talking about that farther on. So just kind of keep this stuff in the back of your mind. All right. Any other questions on matter, states of matter? Alrighty. Well, in that case, we can talk about energy now. And since it seems the theme of our class so far has been dividing all these kind of topics in half, guess what we're going to do here? We're going to divide this one in half as well. We're going to see that energy comes in two major types, which are more discussed in physics than they are going to be discussed here. But we're still going to acknowledge its existence, give it some, talk about some examples of different types of energy. But this is by and large something you deal with in physics, especially this kinetic energy aspect. That's all physics there. But it's, chemistry and physics are not exactly, separate all the time. So, all right, in terms of potential energy, actually, let's talk about that second. Let's do kinetic energy first. Kinetic energy is energy of motion. So something that is moving is got a certain amount of energy associated with it, right? And if I remember correctly, kinetic energy is 1/2 mv squared. Don't ask me, I'm not a physicist. We're never going to use this formula, so don't worry about that. But it's related to the mass and the velocity. So how big something is, how much mass it has, and how much or how quickly it's going. That's the kinetic energy of it. And so it's just the energy of motion. So how much energy is associated with a moving object. And so kinetic energy is used to do all sorts of things, to get us to go from one place to the next, to move molecules along our bloodstreams and into our cells and stuff. All of that is related to kinetic energy, or just throwing something across the room. That's kinetic energy too. Potential energy, though, is energy that can be converted to kinetic energy, but it's currently not. That's a very good definition, I know, very clear, right? That's energy that could be used to move or make something move or something like that. It's just not. It's energy that can be used. It has potential to be used. Uh, there's a couple of types that you might be familiar with. For example, we have gravitational potential energy, which is if you lift something up, you're giving it more energy because it will now expend more energy to fall back down again. And that's why lifting something takes a lot of your energy. You're going to be, physically using your muscles to lift something up. You're expending kinetic energy to build up potential energy in whatever you're lifting. So if I lift Oz up here, here we go. Now he's up here. Do you like the tongue, by the way? His always sticks out. All right, little dude. You have higher potential energy now. Did you know that? And he's like, forget it. I want to be back down there. So that's another doggo for the day. But that's gravitational energy. We also have chemical energy, chemical potential energy. Think of gasoline. Gasoline just sitting there as a liquid. But we know there's quite a bit of energy we can get out of gasoline if we combust it, right? If we burn that gasoline, it's going to be, we can use it to make a car move or a plane or whatever. So, good. So, that's another kind of energy source where we just have energy ready to be used. We can have electrical potential energy as well, like a battery. We can store energy and use it later to make something happen. And these are all potential energy types. One type of kinetic energy would be mechanical. So, having things move to make other things move, like gears and cogs, or like in a car you have the pistons and the wheels and all that. So, you can have that type of kinetic energy. Don't really worry about these. All I ask is that you have read this once. I'm not really going to test you on this sort of thing. So, but we're addressing it just to talk about some last bits here. All right, just so we know, formally speaking, we're going to see that temperature is essentially for us, when we talk about temperature, how hot something is, that is really talking about the kinetic energy of some substance. So the temperature is not really how hot something is. We're going to see later when we talk about heat, it'll be pretty different. When we talk about temperature, we're talking about average kinetic energy. So just so you know, temperature is not heat in chemistry. In lay terms, yeah, you can say, okay, it's pretty hot outside, there's a high temperature. But really what that means is that it's not that the molecules in the air have a high heat, it means that they have a high kinetic energy. So they're moving more quickly. Temp is in fact how quickly things are moving. And so, since we know solids just vibing in place are they have relatively low kinetic energy. Typically, we see solids at low temperatures, right? We know we can get water, a liquid, to turn into ice, a solid, by lowering its temperature, by removing some kinetic energy. So it's no longer able to move around the molecules, they just have to sit there and vibrate in place. And so, just generally speaking, you're more often to find solids at low temperatures, gases at high temperatures. Same thing with water. If we heat it up enough, we've turned it into a gas. Now things are zipping all over the place. So that's kind of our one little distinction that we're going to make. We'll talk a lot more about temperature when we talk about gases, because we're going to see that temperature is a very important property for gases that we can analyze. So But we'll get to that when we get to the gas chapter. Alrighty. Any questions on energy? Alrighty. So, let's talk about quantities. Nope, let's try that again. Quantities in science. In science, numbers don't really mean anything by themselves, right? As you've been, hounded in math class repeatedly, we're always going to have a unit associated with a number. So a quantity in science is always going to come with both of those. Some sort of number as well as a unit. So those two together will equal a useful quantity. Something that we can actually work with. And there's all those memes that we see with the teachers like, if Johnny has 10 apples and loses 2, how many does he have? And you say 13, and they're like, 13 what? 13 polar bears? It's like obvious. But yes, we're going to want to make sure that we have our units correct in all of these numbers that we're going to be dealing with in science. So don't forget there's always 2 parts to a quantity. So a number is 1 part, but you'll need the unit as well. And we're going to see later on that we can change units, which is going to end up changing the number. So it's important that we associate the correct number with the correct unit. But that'll be a little bit longer, or a little bit farther down. We can talk about a few common units. For different measurements, different aspects of things. Something we might talk about is length. How long something is. Typically, for this, we'll use the meter. Notice all of these are meter-based. We'll talk about the metric system later on. But that's kind of how we'll do things in science. We'll use units like these and others, micrometers and nanometers. We'll learn about the prefixes later. In the American system, or U.S. customary imperial, whatever, those are feet, inches, miles, yards. Those are units of length that we'll commonly come in contact with. So we're going to just list a couple of units for different types of things. Another quantity, we can talk about volume. I wonder if you guys can hear that. Can you hear one of the dogs barking downstairs? I don't know, he's kind of quiet, but hopefully that will not be, he's not that disturbing. For volume, those are going to be cubic meters. Or liters. Or as we'll see derivations of, you can hear him. No, yes. Nobody knows if we can hear him or not. So I guess if he's very quiet, then some people can, some people can't. So those are our 2 main units for the metric system, liters and cubic meters. In the U.S. system, we have, quarts, gallons, cups, teaspoons. We have a ton of different U.S. units, but a couple of examples. Those all measure volumes, right? So they're going to measure how much space something is occupying, and then you have those. All right. How about next? Let's do light blue. We can talk about mass. This is going to be kind of another way of talking about the amount of something. We are going to have kilograms, grams. Everything's going to be gram-based for us when we talk about mass. In the US system, we have ounces, pounds. What's lower than an ounce? Grains, stones. These are random British units, right? That don't really make any sense, but I think a stone is 14 pounds and a pound is 16 ounces. That's the part that sucks about the US units, is they're all just kind of random numbers to change between each other. But we're going to see the metric system, everything is going to be just based on powers of 10. It's very efficient that way. All right, let's see. What other quantities do we have, and what other colors do we have? Purple. Okay, purple's next. How about energy? I think... What do we use in the US for energy? Oh, calories, right. Joules and calories are kind of our main units there. We still use calories in science. So it's both of those. So we'll use joules or calories there. What else what other things do we have? Temperature. For us, we'll typically use degrees Celsius or Kelvin. Kelvin does not take degrees. And then the US, of course, they use Fahrenheit. Here's your fun story about Fahrenheit. So, Celsius scale goes 0 to 100 based on the freezing and boiling points of water. Probably one of the most common molecules that we will ever encounter, right? We are mostly water ourselves. So that scale is based on water. The Fahrenheit scale was developed because some random dude in some random city somewhere had set 0 to be the coldest that his city had gotten and 100 to be the hottest the city had gotten in whatever time frame. And so that became the scale for Fahrenheit. So it's just kind of this arbitrary, it happened to be these temperatures. Let's set our 0 and 100 based on that. So again, it's kind of random that way as well, but it's what we're used to, right? So thankfully for us, I'm not going to set us through the tedium of going between Fahrenheit and Celsius. If you really want to, go right ahead. It's what, 5/9 times degrees Celsius minus 32 to get Fahrenheit? No, plus 40. No, that's Fahrenheit to Celsius. Whatever, who cares? It's not something we're really going to ever deal with. But Celsius to Kelvin, we certainly will. So, if you want to go from Kelvin to Celsius, it is simply a matter of taking your temperature in degrees Celsius and adding 273.15. And that will give you its temperature in Kelvin. So that's something you will want to learn. Formula for you here. This one will be important for us later on. Again, I'm not going to really focus on this right now, but if we wanted to, we could say, okay, what is, let's say for degrees Celsius, about the temperature of a refrigerator, we can see how many Kelvin that's going to be by simply adding 273 to it, 0.15. If we do that, we're going to see that this number will be 4 plus 273.15, which will equal 277.15. Notice again, no degree symbol there. No degree symbol with Kelvin. The reason that we don't have a degree scale is Kelvin can never be negative, and it can never be 0. So, well, I mean, theoretically, it can't be 0. 0 Kelvin is what's called absolute zero. And that's when all motion stops. So remember, temperature is kinetic energy, how things are moving, how quickly things are moving. At 0 Kelvin, absolute zero, everything stops moving. It's not something that we've been able to ever achieve. We've gotten pretty close in labs. In controlled situations, we can get close to zero, but we have not gotten actual zero. And it's weird to think about, right? Because solids are vibrating all the time, right? And so at absolute zero, apparently they'll stop doing that. And that's why you can't go negative, right? Because they can't, if they're already not moving, you can't take any more movement away, right? If there's no motion, you can't take any more motion out. So that's why it's defined as zero. So we can never have a negative Kelvin. And we're going to see that's going to be important for us when we talk about gases later on. So just keep that in mind. Celsius and Fahrenheit can totally be negative. No problems there. But not Kelvin. Kelvin cannot be negative. All right. Let's see. What other units do we need to talk about? I don't know. That seems like a pretty good amount, right? Oh, force maybe? Nah, forget it. We're not physicists. We don't care about force. All right. In that case, we're cool with units. So we're going to see that the unit will describe the quantity. Oh, wait, no, there's a couple more. I don't want to talk about that yet. Yeah, we'll just keep going. So the unit will describe to us what the quantity is. And having the correct number with the correct unit will be an important part of chemistry. Later on, we're going to talk about converting in between units, something that you've already kind of done all your life, but we're going to make it a lot more formal, and we're going to be able to illustrate how you can do it between any units of the same kind of type. So, I mean, for us right now, we can all convert between minutes, seconds. Oh, there's one time. Minutes, seconds, hours, days. We know how to convert between them. We know that 1 hour is 3,600 seconds, right? We can do the conversion. We know 60 minutes in an hour, 60 seconds in a minute. Therefore, 1 hour is 3,600 seconds. And we can say, okay, well, what about 1.5 hours? We can go from there. We're going to learn a formal way to do that a little bit later on. All right. But first, I'm going to introduce you to what will probably become the biggest pain in your behind during this class, which is the concept of significant figures. Ho, ho, ho. Those of you who have taken chemistry before will remember these. Often these are just called Sig Figs, or sometimes I'll write SF. And significant figures are a way of communicating. They are how kind of good a measurement tool is. It's essentially how accurate we're able to take a measurement in science. And we're going to see that we're going to have rules for counting the number of sig figs. But let's first talk about where they come from. And so, here is my favorite example. Let's see, what shall we draw? How about today we have a little bee. Okay, so it's got its little things there. Yay. All right, we're going to measure this bee. And let's say I have acquired the world's worst ruler, which only goes from 0 centimeters to 10 centimeters. There are no lines on this ruler because it is a piece of crap. So we're going to see what we have, what we get here. So how long does this be? And so we're going to say, okay, well, apparently its smile extends past its face, but whatever, we can measure there. Because this ruler is a piece of crap, we don't have a lot of information here. So we only know one thing for sure. And that is, we know that this B's length is somewhere between 0 and 10. That's as far as we know. But we don't know anything more about that. And so if we are to try and figure this out, we are going to have to take a guess. And looking at this, I'll say, I don't know, maybe it's about 3 centimeters long. Seems pretty reasonable, right? We know it's closer to that 0 side of things. So I'm going to guess that this B is 3 centimeters long. Not unreasonable, right? But let's take a look at what we might do if we have a not piece of crap ruler. Let's say now our ruler has, okay, I'm going to try and do this as good as possible. Oh no, that's only 4. Okay, let me try again. Drawing rulers is tough. Though I guess I don't have to be that good at this. That's about right. Good enough. So, now my ruler is slightly less crappy. And again, we're pretending that all those are equal. They're kind of equal, right? Good enough. Now, I can see very clearly, right here we have 2 centimeters and 3 centimeters. So, now with a slightly better ruler, we can say that it's between 2 centimeters and 3 centimeters. It's bigger than 2, it's less than 3. Because now our instrument is a little bit better, so we can see we have a better shot of getting this right. And so if we look at this, it looks to me as this B is a little bit closer to the 3 than the 2, right? Maybe just a little bit. So maybe we'll guess that this is 2.6 centimeters. Something like that. 2.6, 2.7, maybe even 2.5. We're guessing. But we know for sure it's between 2 and 3. So we have a better guess than we did before. Let's take a look at it one more time. Where I'm going to actually... okay, hold up. Oh dear. Oh, hey, that kind of worked. Okay. Not what I was planning, but hey, I like it. Alright, so now let's say... Okay. Now we have a slightly better ruler. And so, now we can see, in fact, this line here, oh gosh, that's way too big. Let's see, let's make this super thin. This line here, what is that line? 1, 2, 3. I don't think I have enough lines here. Oh, I think I deleted it. Oh well. That's 2.6. And that line is 2.7. Hopefully, I'll put the other one back in. Oops. We'll put this one back in there. So that's 2.5 right there. Okay, so bearing with me here, we can now see that this B is in between 2.6 and 2.7. And with my drawing as is, I might say it's right in the middle of those two numbers. And so, I might guess, we know it's between 2.6 and 2.7. We know that for sure. We can see 2.6, we can see 2.7, we know where those are. So we know it's in between those. So maybe we'll guess 2.65 centimeters. All right, and so this is reasonable, right? What's important to note here is that as our instrument got better, we get more numbers out of it, right? Would it make sense to say on this very first one, 2.65? Who would guess that, right? You don't know that. You have no way of saying 2.65, 2.72. You have no way. You know it's between 0 and 10, and that's it. So, what's important that we understand is that the last digit, the last number, is uncertain. We guessed. We said, okay, it looks like it's in the middle. It seems reasonable to guess that that last number is a 5. In this last one, we knew it was between 2 and 3, and we guessed 2.6. We're using our best estimate to get that last number, but we don't know it for sure. We don't know that it's 2.6 exactly. And with this one, we're also not quite certain there because our ruler was complete crap. So, what we see here, two things. Here, let's use dark blue. As our measuring instrument improves, we get more accurate numbers. And by accurate here, I just mean we're able to get it closer and closer to reality, right? So we were able to get it closer and closer to what it might be exactly, as we're getting a better and better ruler here. The last digit is uncertain. And so it's understood that we're doing our best when we take a measurement like this, when we're reading a thermometer in chemistry lab, or we're taking a look at the volume in a burette. We're understanding that the last digit is uncertain, and that's our best guess. However, the other digits we know for sure. We could see on this ruler, we know it's between 2.6 and 2.7. So we know for sure that it's 2.6 something. So we are very absolutely confident in our first two numbers, and the last digit there is uncertain. So it's our best guess. And so we're going to see this concept of significant figures is going to address this. By the way, we're going to see that, let's say I had one more step of the better ruler, and when we did this, maybe the next ruler, we got 2.650. It's important that that 0 is there, because now that tells us that this is important, because this is now the uncertain digit. Maybe it looks like it's right on the line, the 2.65 line. Maybe it's right there. And so that's information to tell us, okay, we know now, we know those three for sure. And now the last digit, maybe it was right on the line. And so now that's the uncertain digit. So zeros, as we're going to see, become very important. And so we're going to have rules about these. All right, so your numbers that you get out of your measurements, super important that we have the right number of numbers as we go along. We have enough numbers to tell what we do know, and we have one number to tell us what we don't know. All right, and that what we don't know, again, we're not going to guess something completely crazy. We're going to guess something reasonable, right? And so maybe when you looked at that ruler, you said, oh, you know what, I think it's 2.66. And someone else says, no, it's 2.64. And that's totally okay. That last digit is uncertain. And so all of those would be acceptable answers. If you say 2.69, that might be pushing it, because now it's like, is it that really that close to 2.6 or 2.7? You know, that's a little bit more of a stretch, but, you know, a cluster of answers like this are fine. You're going to see that you're going to have an assignment later where you're going to be taking some measurements like this, and there's not going to be an exact right answer, right? Anything that's reasonably close is fine for a measurement like this. All right, but I am looking that you're getting the correct number of digits. All right, and so notice also with that uncertainty, we know that we always read an instrument like a thermometer one more decimal place than we can see. So notice that first ruler went from 0 to 10, and that was it. So we saw the tens unit. So we had guessed the ones unit. When we had a ruler that had ones marked out, we were able to guess to the nearest tenth. And then on that last ruler, where we were able to see the tenths, we could see 2.6 and 2.7 tenths place, we guessed to the hundredths place. So we always go one more spot than we can actually know for sure. And again, that's going to be that uncertain number at the end there. So let's do one more kind of example of this. If I have my thermometer, give me a second to do this. That's way too far. Okay, here is our thermometer. Okay, let's read this thermometer. So, we see in this thermometer that we have graduations or little kind of increments of 1 degree Celsius, right? We can see 21, 22, 23, 24, right? So we can see the ones place, which means we need to read this measurement to the tenths place, one more decimal over. So we can see 21, 22, 23. We cannot see 21.1, 22. Or sorry, 21.2. We can't see the tenths place. So that's where we're going to make our guess. And so, again, we know this is between 23 and 24. We know it's between those two. We can see it. We see where 23 is. It's past 23, but it has not reached 24. So, we're going to guess. And let's say, to me, it looks like it's a little less than halfway. And so I might guess, okay, well, I know it's bigger than 23. And it's not quite halfway, but it's almost there. So I might guess 23.4. Oops. Oh, that worked. Okay. Degrees Celsius for this measurement. Again, with the understanding, we know this for sure. And this one here is our best guess. All right, would it make sense to say 23.35? No. We have no evidence to say it's greater or less than 23.4. We don't have that evidence. We don't know where 23.4 is exactly. So we can't say it's less than 23.4 and just a little bit less. It doesn't make sense to do that. So it's always one more decimal place than you have explicit information. All right, and again, you're going to have a homework assignment on this. So just keep that in mind as we go through here. All right, enough of that for now. So now that we've seen all this information about how to measure things and get numbers out of measurement instruments, we're going to see that the numbers we get out will have significant figures. And those are later on going to affect any math we do with those numbers. But for now, if we want to identify how many significant digits are in a number, we can do that. And so, when we're looking at the number of sig figs that a number will have, first thing we want to do, our kind of main rule is that all non-zero digits are significant. So if we take our three measurements we did on that B, we see, okay, this first number has one significant figure. It's just one number. All of these are non-zeros. Non-zero numbers are always significant. So we're going to see that this one has two significant figures, and this one has three significant figures. The more significant figures you have, the better the measurement is. And that also says the better the instrument was. Or more expensive, right? So the instrument that we use to make that measurement, whether it's a thermometer or a ruler or whatever, the better if you want better numbers out of it, you're going to pay more for a better thermometer, right? You'll want a nice digital one that can read 0.001 degrees Celsius or something if you really want a very accurate measurement. So the more sig figs you have, the better your measurement is. And so it's important, it will be important later on that we understand how many sig figs a number has. Because that's going to determine, again, some rounding stuff when we are going to be multiplying numbers later on or adding them or whatever. So this will be important. Alrighty. So hopefully everyone can see non-zero numbers are significant. We've seen those numbers, we've made our guesses, and we're good. Zeros, though, are where we're going to have trickiness. The reason is sometimes 0 is a placeholder, but sometimes it is part of a measurement. We saw that something was right on the line. That 0 might be part of a measurement. But sometimes 0 is just a placeholder. And if it's just a placeholder, it's not going to count towards our number of significant figures. All right, and so we're going to see that we have 3 rules here. Rule 1 for zeros is any leading zeros are always placeholders. Oh dear, I'm out of space. Okay. Placeholders, which means that they are never significant. So, because if I really wanted to, we'll talk about what a leading zero is in just a second. If I really wanted to, I could say, oh yes, this measurement is actually 003 centimeters. Don't I sound fancy? But who cares? Nobody starts a number with 0 like that, right? Unless you're James Bond, I suppose. But not something that we see. No one's going to write 2.6. Like, it just doesn't make sense. Although those are placeholder zeros, they have no impact on our measurement, right? Nobody cares that that 0 is there. And so those zeros are not going to be significant. Even if I take a number like this, those zeros are just placeholders. They're there to tell me that that number is really small, right? But they don't actually have any information about the measurement. So those zeros, which are called leading zeros, they don't count for our sig figs. So this number 003 is still one sig fig, right? I can throw as many zeros in the front as I want. It doesn't change the number, but it doesn't add anything either. So there's no point in having those there, besides being placeholders. We're going to see that this number here would have 2 sig figs, as will this one. Since these are just non-zeros, we're not going to count the zeros as significant there. Okay, so they're there for placeholder purposes. They're never going to be significant. All right? Next one. Any zeros in between significant digits are part of a measurement. And therefore, those are going to be always significant. So let's say I've measured something and it's 104 centimeters. That 0 there does matter because it's part of my measurement, right? I have found out that this thing is between 100 and 110 centimeters, and I have guessed it to be 104. And so that 0 there is part of my measurement. I know that it's above 100, but below 110. So that number is part of my measurement. That 0 will always be significant. Let's just have some more random numbers here. All these zeros in between significant digits will always be significant because they're a valid part of our measurement. So, if we're looking at these, all 3 of these digits matter. With this next number, though, we have 2 different types of zeros. We have zeros that are leading, one's at the start of the number, and we have one that's in between. Remember, zeros at the start are placeholders. They do not count. Zeros in between are part of a measurement. They always count. So this number here will have 4 sig figs. These 2 here are leading, and so they're not significant. Those 2 zeros there at the start do not count towards our significance. All right, the next one, we have zeros that are in between significant digits here. All 4 of these are going to be significant. All right. So these 2 are the easy rules. Well, the other one's not bad, actually, but that's the last rule tends to be the one that sparks the confusion. So, zeros in the front, never significant. Zeros in between, always significant. Trailing zeros. They can be either placeholders or measurements. And so they are sometimes significant. And of course, nobody likes, well, sometimes. What the hell does that mean? We see that we have a rule. A trailing zero, any trailing zeros. Ooh, that's really ugly. Trailing are significant if there is an explicit decimal point anywhere in the number. Otherwise, if you do not have a decimal point, they are placeholders. And we'll take a look at what that means. So, let's say I take my elephant and I put it on the scale, and the scale says, you know what? It's 12,500 pounds. I have no idea how much an elephant weighs, but we'll say it's that much. This scale is pretty cheap, and it has read these digits for me. Looking at the number it churned out, it does not have a decimal point. So that means zeros at the end are not significant. So these two zeros here are not significant, which means that this number has 3 sig figs. But let's say I take my elephant, we go over to JPL, Jet Propulsion Laboratory, over in Pasadena. I guess I'm still in LA. I'll be in Ridgecrest later today, but it's a NASA place. So they have a very fancy scale, and their scale can accommodate my elephant. And when we put it on, we get this measurement out. And so we now have a decimal in our number. And so, again, that means if there's a decimal anywhere, zeros at the end will be significant. So that means everything here is significant. That is 6 sig figs. All right, so if I've gone to a fancy scale and it has measured all those pounds, there we go. And it says 0.0 for a reason, to indicate that it has measured everything up till here, and this is the uncertain one. In here, this is our uncertain one. The other zeros are there to placehold, to tell us it's 12,500. If we left those zeros off, we would have 125 pounds. And what elephant weighs 125 pounds? That doesn't even make sense. So those zeros in the first number, they matter to tell us how big the number is, but they're not part of our measurement. So they're placeholders. They have a purpose, but they're not significant for us. We used a crappy scale, and so we get a crappy number out. When we go to NASA and we have our fancy scale, we have a more exact number, and so those zeros will matter now because we have a more precise instrument. All right, so the rule here is if you have a decimal anywhere, ending zeros will count. All right, let's take a look at a few numbers here. What's our time? Oh, we still have 10 minutes, okay. All right, let's say will be the same, why not? Okay. Looking at these numbers now, you got all sorts of zeros here. So, let's recap quickly. Zeros at the front, never. Zeros in between, always. Zeros at the end, yes if there's a decimal. All right, so for the last category there, you're looking if there's a decimal anywhere. Any decimal point means all trailing zeros at the end, will be significant. So, here we go. First things first, of course, we see non-zeros, always significant, right? We have 2 more zeros in this number. First one we see there is in between numbers. In between numbers is a yes. That is a significant digit. We also have a 0 at the end. We need to now search our number for a decimal point. I do not see a decimal point, which means that 0 is not significant. It's there as a placeholder. Still important for our number, but it is not a significant figure. Not a significant digit. So this one has 3 sig figs overall. And just to make sure we're really clear about the purpose of placeholders, hopefully we see those two numbers are not at all the same. That 0 makes a big difference. Imagine on your paycheck, instead of getting $2,060, you got $206. You'd be pretty mad, right? That 0 is super important. It's just not a significant figure. All right, so don't just think of who cares about these zeros. They're not significant. They definitely matter. All right, you're going to see on one of your things where we're talking about rounding. Oh, forget it. We haven't talked about rounding yet. We'll deal with that later. So just keep in mind, those two numbers are not the same. They both have 3 sig figs. Whoop-de-doo. But not the same number. No one wants a paycheck that is 1/10 of what they thought it would be. What color am I using? Blue? I think so. Alright, next one. Non-zeros. Let's look at the zeros we do have. We have a 0 in between, so we know that one's significant. We have a 0 at the end, so we have to look. Do we have a decimal? Aha! We do have a decimal here. And that decimal will tell us that that 0 there counts. That's a significant 0. So this number has 4 sig figs. All right. Next number here. Start off with our non-zeros. We know those are significant. We got 3 types of zeros now. We have zeros at the front. We have zeros in between. We have a 0 at the end. So, zeros in the front, never ever. So those are not significant. Our next 0 is in between. In between is always a yes. And then now we have a 0 at the end. So we must search our number. Do we have a decimal point somewhere in this number? We do. We have a decimal point there. So that 0 is there to tell us it's part of the measurement. And so that counts. All right, so anywhere in the number, if you have a decimal, that's when your trailing zeros will count. All right. Any questions on these examples? Do I want to talk about rounding now? I don't think I do. I think we'll do rounding next time. Yeah. Okay. Well, in that case, I think this is a good place to stop for the day. We'll pick this up again next week on Tuesday. We'll have our next bit there. I'm going to go ahead and I'll post your homework today, but we have not covered everything, so I'm not going to make it due a week from now, okay? I'll make it probably due a week from Tuesday. So you'll have 5 plus 7, 12 days to get working on it. So I'll go ahead and post that. How the homeworks work. Many of the homeworks I used for both your classes are worksheets. These worksheets are actually designed for group work. So they're going to say things like, talk amongst your group members and do X, Y, Z. You can ignore that. If it says something that's like, talk about your group and find out how well you worked as a team. Stuff like that. There's no team, right? So, it's because it's individual. So we ignore kind of like team progress kind of questions. If it's like talk with your team and talk about a important aspect of this worksheet or whatever, still do that. Like if it's still asking you something like that that you can answer, go ahead. But if it's like how well is your team working together, or does your team have any questions, go ahead and ignore those because there's no team. You'll also ignore where it says, read assigned pages or whatever. It'll say that at the end of almost every worksheet, there are no assigned pages, right? So you don't have to worry about that. Ignore those as well. And I guarantee you, we're going to see on Discord, people are going to be like, what do I do with this reading the assigned pages? And so when you, as responsible students, see other students asking that, you can go ahead in Discord and say, hey, you don't have to do that. Don't worry about it. Skip it. So, in case I'm not available to respond right away, you guys can do it. I'm empowering you as peers to be able to communicate directions to each other. So stuff like that, that's obviously not answerable and not really applicable, skip it. You might see like memorize the elements as well. Obviously, you do not need to do that. You're always going to have access to a periodic table. That being said, though, it is beneficial to kind of have a rough familiarity with them. This week is just Tuesday's one, so you don't have to do anything more this week on Discord if you don't want to. And as for points, there are not points for participation. Participation prevents you from being dropped, so it's worth more than points, right? So as long as you are somewhere on the Discord this week, you're good. If you've already said hello and that's all you said, that's fine. That's all I asked for this week. So you'll only have one thing per week, so you don't have to do a separate Tuesday or Thursday or every day. No, don't worry about that. It's asynchronous, so some people are not going to watch these videos until Sunday, which is fine. That's totally cool. And so I'm not going to be like, well, you didn't respond on Wednesday, so you're out of the class. No, don't worry about that. That's why I'm giving you, at least a week for your homework as well, because I understand people may not be watching these as I'm recording them, or even the same day or same couple of days. So totally understandable there. Ignore all that stuff that you're going to see. Okay? So yeah, I'll go ahead and make that available. What else do I want to do? Oh, yes. For kind of just other things you can be doing in the meantime. In Discord, let's see, I've got it actually. Let me write it out and then I'll pop over. Start memorizing your metric prefixes. That's like kilo and milli and that sort of thing. And you'll also start wanting to learn your polyatomic ions. You'll want to memorize those. For example, you'll be wanting to learn the formula and the name of a bunch of polyatomic ions. And so for 111 students, you're going to need those ions sooner. For 101 students, that's a little bit later on in the course. That'll be chapter 5 for us. But I guarantee you, the faster you start learning those, the much easier time you're going to have when we start talking about naming compounds. So those are both in Discord for us. If you go to your handouts thing, for example, here are your metric prefixes. I really only want you to go between, let's say, giga and nano. The others you're not going to really need because they're absurdly large or absurdly small. So kind of focus your memorization efforts between giga and nano. So you'll want to know the name. You'll want to know that letter abbreviation there, the symbol for it, as well as the power of 10 that it represents. So I want you to understand centi, which is abbreviated C, means 10 to the minus 2 power. All right, so those are the things I want you to start learning with this, okay? It's also in the 111 somewhere. It'll probably be closer to the top. And then you'll also have this summary of ions. Let's see if I can take a look at that. That's going to have our list of polyatomic ions here. So not on the first page, but the second. Everything in this chart here that you see called polyatomic ions, you're going to want to start learning all of those chemical formulas as well as their names. And pay close attention to the names because a lot of them are very similar. Nitrite versus nitrate, they are similar, one letter difference, and that makes a big difference chemically speaking. So start learning those. Flashcards are a good idea. This chart here is going to be very, very useful for you. So again, 111 students, you're going to need this probably next week or maybe the week after, so you'll need this soon. 101 students, you have a little bit more time. We're looking at chapter 5 for this. We're on chapter 2A right now for 101. So we have some time, but again, the faster you do it, the better, especially right now since there's not much going on homework-wise. All right. Any questions on that? Those charts are in Discord for you to take a look at. They're either in handouts or extra resources. And again, you'll probably have to scroll up for those, just because I have the same stuff from last semester or 2 semesters ago or whatever. Last time I taught these that are in there, so you might have to scroll up a bit, but they're in there. So, alrighty. Enjoy your weekends. Again, I'm going to post your homework so you can start on it, do the stuff that we've gone over, but that's not going to be due for at least another week. All right. How homework works, it's PDFs on Canvas. You'll take them, print them out if you can, write on them, and you're going to take pictures and upload those back onto Canvas. If you don't have a printer, you can just write your answers on a separate sheet, but kind of like make sure that everything is like labeled clearly so I know what part you're talking about. Don't just like write number 117 or something. You know, just give me a little more information because I don't have the answers memorized, right? I have the questions and answers work together. So, alrighty, that's enough for today. Whew, excuse me. I'll see you on Tuesday. So enjoy your weekends. Have fun. Take care. Any questions, throw them on Discord over the weekend. So have fun. See ya.